Today we are going to start on thermal performance analysis of the building. In the last two class on this particular topic, we have discussed about the sustainable building. Then we discuss on energy conservation in buildings. Today basically we will do the thermal analysis, performance analysis of the building. When we look the building, then we look the heat balance of a building. Now the heat balance of a building refers to the equilibrium between the heat gain and the heat loss within a building. So a building maintains a stable indoor temperature when the total heat gain is equal to the total heat loss. Now if gain exceeds the losses, so building warms up. If the losses exceeds the gain, then the building cools down. So the concept is fundamental in building thermal analysis, HVAC design, and energy efficient building design. Now the heat balance of a building is a relationship between all heat gains and heat losses, and that determines what will be the indoor thermal condition, and that will again decide whether we need for heating or cooling of the building. Now if we look what are the different way the heat gains in the building, obviously the solar heat gain, internal heat gains, and infiltration and the ventilation gain. What are the typical losses from the building? The conduction loss, ventilation loss, and the radiation loss. Now if you look in this picture, this is a building. So your solar radiation falls on that building, and that radiation comes inside the building and it brings heat inside the building. There are people working in the building, there are certain equipments up there, so that also release certain amount of the heat, what we call an internal heat gains. And there can be leakage through which also heat can come inside the building. What are the different losses? You can see there is a conduction loss, there can be evaporation loss, there can be radiation loss, and these two has to be balanced. That amount of the heat gain inside the building must be equal to the heat losses from the building. And in this class, we basically try to understand how these heat gain and heat loss are estimated or calculated. Now, if you look the heat exchange between the building and the environment, a building constantly exchanges the heat with the outdoor environment through several processes. Obviously, first is the conduction. Heat flows through building components such as walls, roofs, ceiling, and floor. And this occurs when there is a temperature difference between the inside and the outside. If say outside temperature is 35 degrees centigrade, inside temperature is 25 degrees centigrade, so obviously the heat will come from outside to the inside. Now if the outside temperature is 5 degrees centigrade, it is a very cold climate, you are keeping the inside temperature is 25 degrees centigrade, in that case heat will goes from inside to the outside. Like here example, on a hot day, heat moves from the hot exterior wall to the cooler interior. Second process, the convection. The heat transfer occurs between the building surface and the moving air. Air flowing over the surface carries heat away or brings heat in. This will be always a vice versa, whether we are looking at heat gain or we are looking at heat loss. When we are talking a warm and humid climate, basically we try to understand the heat gain. When it is in a cold environment, then basically it's a heat loss. Now, example, wind outside a building increase the convective heat loss or gain. Third is the radiation process. Heat transfer occurs through electromagnetic waves without direct contact. The building exchanges heat with the sun, sky, and the surrounding surface. Say sunlight hitting the roof or the walls. Solar radiation through the windows. Solar radiation can pass through the transparent materials like glass window. It is then absorbed by the internal surface such as floors, walls, and furniture, and that also increase the indoor heat gain, and this is typically known as solar heat gain. There can be evaporation. Water evaporation removes the heat and creates a cooling effect. And that example, evaporation from plants, say indoor plants, are the sweat evaporation from the occupant. Now, if you look the internal heat gains, the heat inside the building also comes from the internal sources, like human occupants, lighting system, electrical appliances, equipments, and these all sources increase the indoor temperature. So that's also heat gain. Now, heat exchange between the human body and the indoor environment, because human body exchanges the heat with its surroundings through four mechanisms: convection, radiation, evaporation, and conduction. Now, if you look this particular photographs, this is the person. So there can be a conduction when we are touching the floor. There can be evaporation, like we are sweating, and that is evaporating. There can be radiation from the body, and also if there is an airflow, so there will be convective heat transfer. Now, thermal comfort and human sensation. If heat loss occurs, the body loses heat to the surrounding, and a person feels cool. But if the heat gain occurs, the body gains heat from the surrounding, person feels hot and begins sweating. Now, humans themselves generate heat due to the metabolic activity. When we do certain work, so part of the energy, generated energy, is used for the physical work, and the remaining heat is released to the surrounding to maintain the body temperature approximately 37 degrees centigrade. So now if you look, you are sitting inside a classroom and you are doing some gym activities inside the gym. So inside the gym, due to the more physical work, the heat released from the body will be much higher rather than sitting inside the classroom. Now, when we look the thermal performance of a building, the thermal performance of a building refers to how well the building maintains a comfortable indoor temperature while minimizing the heating or cooling energy. The thermal performance of the building depends on design variables, material properties, weather condition, and building uses. And these factors determine the heat balance of the building. Now, engineers generally use steady state method or dynamic method or correlation methods, ranging from simple hand calculation to detailed computer simulation to analyze the building performance. So, what are the factor affects the building thermal performance? Here you can see in the figure the heat balance in the building. It will depends on the material properties, that means building material property. What are the physical properties like density, specific heat, conductivity? It depends on the climatic data like solar radiation, ambient temperature, wind. It depends on the building design data, how the building is oriented, number of windows, walls, what is the area of the window with respect to the wall area, and the occupants, the habitats or occupants inside the building, like internal heat gain, air exchange rate, or is there any heating power, etc. So the design data, these are basically architectural and geometrical characteristics of the building. Here the size and shape of walls, roofs and windows, building orientation relative to the sun, window placement in area, and the shading device such as overhangs, louvers, or the trees are there in the buildings. The impact, the proper design can reduce the solar heat gain in summer and increase the solar gain in winter, and it also improves the energy efficiency. Now, if you look the material data, this refers to the thermal characteristics of the construction materials. Basically, the properties like density, specific heat, thermal conductivity, and transmittivity. Thermal conductivity, because it's the ability of the material to conduct the heat. If the thermal conductivity is low, say if it is a wooden wall, wood is a very poor thermal conductivity. So the heat will comes relatively lower than if you have an aluminum wall, which is a very high thermal conductivity. Transmittivity, where the ability of the material like glass to transmit the solar radiation. Now, if the transmittivity is low, so through the glass, the less amount of the solar radiation will come inside the building. So the impact, materials with high thermal mass store heat and stabilize the indoor temperature. The climatic data, that is the external climatic conditions, strongly affect the building heat transfer. So obviously the solar radiation, outdoor air temperature, wind speed, and relative humidity. Examples: a building in hot climates requires shading and ventilation, while the cold climate needs insulation. So the impact the climate determines the heating or the cooling requirements of the building. Building uses data, these are the internal conditions related to how the building is used, like occupants, the body heat, lighting system, electrical equipment, air exchange, or the ventilation. And this creates the internal heat gains, which also influence the cooling load. Now, what are the different methods to estimate the building thermal performance? There are lots of analytical methods are used to evaluate the building performance. The steady state method, where assume the condition do not change with time. These are generally the simple calculation. It provides the average heat load or temperature, often calculated on monthly or annual basis. It's simple and suitable for hand calculation. When you look the dynamic method, it considers the time variation of the temperature and the solar radiation, more realistic and accurate. So when we are looking the solar radiation data from the morning to the evening, the solar radiation is not constant. In the morning, solar radiation value will be relatively low. The noon time it will be the maximum, and in the evening it will be the minimum. Now, if you take that time dependent solar radiation data, or based on the solar radiation, your ambient temperature also changes. So you are looking at time dependent ambient temperature data. So that can be used in a dynamic method. When we look in steady state method, basically we look what is the average solar radiation, what is the average temperature. So dynamic methods are more realistic and accurate. However, it requires detailed input data. It provides hourly or daily result, and we need computer-based building simulation. So there are lots of energy simulation softwares are available by which we can do the analysis on the building. The correlation methods based on the empirical relationship derived from experimental data. These are simpler than dynamic model and provide an approximate performance estimates. Now let's look the heat transfer process through the wall. So in this figure, this is a wall. So the heat transfer process we are trying to understand. With the solar radiation on the outer surface of the wall, this is the outer surface of the wall. Radiation falls on the wall. Some amount of the radiation reflected back. Some amount is absorbed, and that absorbed energy is conducted through the building and it goes inside the building. Inside the building, through long wave radiation, it radiates that energy or the heat. And convection also, it circulates that heat within the interior or indoor environment. If you look, when we discuss about the solar passive architecture, we call there are 5 design features. One is the absorber, aperture. Now here, this absorber, so this building materials is very important. If it is very polished surface, so whatever the radiation comes, most of the radiation will reflect it back. What is the color of this wall? There will be dark color or it can be light color. If it is a dark color, more amount of the radiation will be absorbed and less amount will be the radiation reflected back. So this wall is very important to understand what is the amount of the heat will gain inside the building or how much protected it will be. So here you can see the radiation on the outer surface of the wall. The first is the reflection. A portion of the incoming solar radiation is reflected back to the environment. The amount reflected depends on the surface color and the reflectivity of the wall. So white walls reflect more radiation, dark walls absorbs more radiation. Absorption. The remaining solar radiation is absorbed by the wall material, and this absorbed energy is converted into heat and raises the temperature of the wall. What will be the heat loss from the outer surface? Some of the absorbed heat again lost to the outdoor environment through convection process. Heat transfer from the wall surface to the surrounding outdoor air, and that will depends on what is the wind speed. If the higher wind speed, that will have more convective heat transfer. If the wind speed is very low, convective heat transfer will also be low. The radiation, the wall emits long wave thermal radiation to the surroundings and the sky. You see, this is the long wave radiation which comes from the external wall. Heat conduction through the wall, the remaining heat moves through the wall thickness by conduction. Part of the heat is stored in the wall material, that's called thermal storage, and that increases the wall temperature. The remaining heat continues to flow towards the inner surface of the wall, and this is why the thick wall can delay the heat transfer into the room. Then heat transfer from the inner wall surface to the room. When the heat reaches the interior surface of the wall, it enters the room through convection. Heat transfer from the wall surface to the indoor air, or radiation. Heat is radiated from the wall to the other interior surface, such as floors, ceiling, furniture, or other walls. And this increases the indoor air temperature. Now, radiation exchange inside the building, inside a room, surface also exchange heat by mutual radiation, wall to wall to roof, wall to floor. And this exchange redistribute the heat inside the room. Now, with all this process, it has an effect on indoor temperature. And that will determine what will be the indoor temperature, what will be the surface temperature, what will be the thermal comfort of the occupants. And if too much heat enters the room, indoor temperature increases and occupants feel hot and uncomfortable. Now, there are two important nomenclature. One is called time lag, another is called decrement factor. Time lag and decrement factor are two important concepts in building heat transfer, especially when studying how heat from the outside environment passes through the wall or roofs into the interior. These are used in thermal performance analysis of the building. Now, the time lag is a delay between the peak outdoor temperature and the peak indoor heat flow through a wall. So, it basically the time difference between the maximum outside temperature and maximum inside temperature. Now, let's consider in a summer day, outside temperature becomes very high, say 35-40 degrees centigrade at 2 o'clock. Now, that maximum temperature you observe at 2 o'clock at outdoor environment. Now you also measure what is the indoor temperature, and you will find the maximum temperature at the indoor environment occurs at 6 o'clock. And this difference in the time is called time lag of 4 hours. Now this will depend what kind of building materials are used for construction of the wall. What is the thickness of the wall? So if it is in heavy materials like brick, concrete and stone, the time lag will be relatively longer. If it is a light materials like metal sheet, thin panels, say in our Assam type building, if it is a bamboo thatch, then you will find a low time lag. That means the maximum outdoor temperature and the maximum indoor temperature at which time these two occurs, and difference between these two time is the time lag. Now, this is a very significant. Large time lag is good for hot climates because heat enters the building later in the evening and indoor temperature stays more comfortable during the daytime. Now, at the evening, again the radiation is not there, so outside temperature is dropping, but your inside and that means you are not getting any heat from outside to inside, and indoor temperature will be more or less constant. Decrement factor represents the reduction in the amplitude of temperature fluctuation as the heat passes through the wall. So it's a indoor temperature amplitude divided by the outdoor temperature amplitude. Now, say for an example, outdoor temperature variation is 12 degrees centigrade and indoor temperature variation is 3 degrees centigrade. So your decrement factor is a ratio of these two. So 3 by 12 is 0.25. Now, lower decrement factor means better thermal performance. Thick or dense walls actually provides you low decrement factor, If it is a thin walls, it's a high decrement factor. So basically the time lag is a delay of the heat. Decrement factor is a reduction of the heat amplitude. And these two factors are very important when we look the design of the wall. Because as in a hot, humid climate, our always target will be how you can have a higher time lag. So decrement factor and the time lags are important in case of the design of a building wall. Now let's look this figure where I have shown the outdoor temperature and the indoor temperature variation. So the outdoor temperature curve, this blue curve, it's a larger wave, higher amplitude. That is obvious. And it represents the outdoor temperature variation during the day. Indoor temperature curve, the light yellow, smaller amplitude shows the decrement factor, reduction in the temperature variation, shifted to the right. Now here you can see the maximum is occurring say at 2 o'clock, whereas this case the maximum is occurring maybe at 7 o'clock or 6 o'clock. So basically you are shifting the maximum temperature and there is a drop. Here the maximum occurs say roughly 35 degrees centigrade, whereas in case of the indoor, the maximum occurs say maybe 31 degrees centigrade. So time lag, horizontal distance between the outdoor peak and the indoor peak. Decrement factor is the indoor temperature amplitude divided by the outdoor temperature amplitude. So from this graph, the amplitude is 8 degrees centigrade for outdoor, whereas in case of the indoor is 3 degree. So the decrement factor is 3 by 8, 0.37. Indoor peak occurs about 4 hours later, so the time lag is 4 hours. The physical interpretation, good thermal walls have high time lag, low decrement factor, and this means heat enters later and indoor temperature fluctuates less. Let's look these two examples. The first case is a brick wall of 230 mm with plaster on the both sides. This is the figure. This is the brick wall and there is a plaster on the both sides. Now if I calculate what is the thermal transmittance U value or overall heat transfer coefficient, this is 2 watt per meter square Kelvin. And it tells the time lag is 8 hours, decrement factor is 0.35. Another example with the brick wall of the same 230 mm with 50 mm insulation on the external side. Here you can see we have put in this yellow line. This is the insulation. Now what is the thermal transmittance? As we have put an insulation, so your thermal transmittance has come down to 0.57. The time lag has increased 11 hours and the decrement factor also drops to 0.18. That means this thermal insulation actually reduces the thermal transmittance. That actually helps to improve the time lag and also it helps to reduce the decrement factor. So the same wall, now we are manipulating, putting up a insulation on the exterior side to manage the time lag and the decrement factor. Let's look some more examples. Now the first case, the external side cement plaster is 10 mm in these examples. This is an external side, we have a cement plaster 10 mm. Then we have a brick wall that is 115 mm. Then there is an internal plaster 10 mm and there is a white paint outside that is 2 mm. Now this is the complete wall. Now if I look what is the U value of this wall, that comes 2.77 watt per meter square Kelvin. Now if I want to calculate the heat gain, considering there is a delta T of 10 degrees centigrade, that means outside temperature is 35 degrees centigrade, inside temperature is 25 degrees centigrade. So the delta T is 10 degrees centigrade. Now what will be the heat gain? Q is equal to U A into delta T. Now here A we are not considering because it is a meter square. So Q is equal to basically U into delta T. So it comes 27.7 watt per meter square. Let's modify the building assembly. Instead of wall, we have a solid brick wall, 115. Then I have put a hollow brick wall. Hollow brick wall means these are all air. So overall thermal transmitters comes down. Then you have the plaster and you have the white paint. So it's a 15 mm wall, brick wall. Then you have a hollow brick block. Then you have a plaster and then you have a white paint. What happens? The overall U value has come down 1.54 watt per meter square Kelvin. The heat gain, considering same delta T 10 degrees centigrade, it is 15.4 watt per meter square. If I compare these two, so there is a heat gain reduction in the order of 44%. Let's look the third assembly. Same, we have a solid brick, externals plaster, then we have an insulation of 50 mm. Then we have a hollow brick. Then again you have a plaster and then you have a white paint. And in that case, your whole assemblies, the U value has come down to 0.53 watt per meter square Kelvin. And the heat gain is 5.3 watt per meter square, or heat gain reduction roughly 81%. So instead of this first assembly, if I go for the third assembly, my heat gain through this particular wall has come down by 81%. And that means if you look the cooling load requirement, so your cooling load requirement will come down by 81%. That means there will be energy conservation.
Sir, how it is calculated, sir? Heat gain reduction.
I will come on that. Heat gain reduction, you can calculate it simple. This is your heat gain minus this divided by this, so this will 44. This minus this divided by this, so you will get an 81%. Now heat gain is calculated Q is equal to U, this U, into A, area, into delta T. Now area I am not considering because I have written per meter square. So basically Q is equal to U into delta T. Now U is 2.77 into delta T 10. So 10 into 2.77, so 27.7. 1.54 into 10, so 15.4. 0.53 into 10, so 5.3. So basically what you are doing, you are basically trying to manipulate this U value. What is the overall heat transfer coefficient? Your always target will be how I can reduce this overall heat transfer coefficient. How you can do? What kind of building materials are using? What is the thermal conductivity of those building materials? Can I put an hollow brick block? Can I put an insulation material? And by doing this, basically you are changing this U value in all these three cases. We'll come again the calculation of the U value.
Okay, sir.
There is, there is another parameter which is called Sol air temperature. Sol air temperature is the equivalent outdoor air temperature that produces the same heat flow through a wall as the combined effect of solar radiation and outdoor air temperature. It is the equivalent outdoor temperature that includes the effect of radiation on a building surface and produces the same heat flow as the combined effect of the radiation and outdoor temperature. Now, when we look at outdoor ambient temperature, say 35 degrees centigrade, now what is happening? Radiation falls on the building wall. Building wall will absorb the heat from the solar radiation. What will be the temperature of the wall then? It will not be 35 degrees centigrade. It will be more than that because it absorbs the radiation. So if it absorbs the radiation, that means your temperature becomes higher. So when I'm calculating delta T, so delta T is not exactly the outdoor temperature minus indoor temperature. It should be more scientifically, it is just T solar air temperature minus T indoor temperature. Now the formula is T naught, that's the outdoor air temperature, you see, or that's the ambient temperature. Plus there is a factor like this, alpha ST by H naught. Now, alpha is the absorbability of the surface. ST is the solar radiation intensity, and H naught is the outdoor surface heat transfer coefficient. Now, if the alpha is more, so alpha ST by H naught will be more. So, absorbability of the surface is more. So, this factor will increase. If the radiation is more, again it will increase. If H naught is higher, then this factor will comes down. Now H naught will depends on what is the outdoor wind speed. That actually makes the convective heat transfer coefficient. If outdoor wind speed is higher, your H naught will be higher. So that's why in our solar building, solar passive building case, when we were putting the design parameter, one was the absorbability. Aperture, absorber. Now absorber means this wall. Now this wall absorbability will depends on what kind of surface you have. If it is a very polished surface, that means absorbability is low. If it is a dark color, your absorbability is high, and that will depends on this alpha. Now if the radiation you talk about ST, now building wall is completely open to the solar radiation. Now you have a plant or you have a tree near the building wall, so the wall doesn't receives the direct solar radiation, it only receives the diffuse solar radiation. So your ST value comes down. So your T sol layer will be close to T naught. Another parameter that is minus epsilon delta R by H naught, where epsilon is the emissivity of the surface, delta R is the difference between the long wavelength radiation incident of the surface from the sky and the surroundings, and the radiation emitted by a black body at ambient temperature. Generally, on a vertical wall, we omit or you approximate this term, but when you do the calculation for the roof, say RCC roof, in that case, we need to include this term. Now, this solar temperature is very important because when I'm looking the cooling load calculation, so in that time your delta T will not be T ambient or T outdoor minus T indoor. It will be T sol air minus T indoor. And you can see from this equation the T sol air will be much higher than the outdoor temperature. So it basically used heat transfer process through walls and roofs, thermal performance of the building, or HVAC design. Now there is something called cool roof. A cool roof is a roofing system designed to reflect more sunlight and absorb less heat than a conventional roof. This helps keep the roof surface and the building interior cooler. Now, properties of the cool roof: it has a high solar reflectance, reflects a large portion of the sunlight back to the atmosphere, high thermal emittance, release the absorbed heat quickly, and these properties reduce the heat gain in building. How it works? Sunlight hits a normal roof. Normal roof absorbs most of the solar heat. Roof temperature can reach to 65 to 80 degrees centigrade. In case of the cool roof, reflects the maximum amount of the sunlight. Roof temperature stays around 35 to 45 degrees centigrade. So if we look this delta T, again in this case, what is the roof temperature and what is the indoor temperature? So delta T in case of the normal roof is very high, whereas in cool roof it is much lower. So you have less heat enters the building. There are different type of cool roofs, like reflective coating roof, where white or light color paint on the roof. Cool roof tiles, special reflective tiles, ceramic or coated materials. Single ply membrane, reflective plastic membrane used on flat roofs. Green roofs, vegetation layer on roof provides the natural insulation. So the benefits of the cool roof: it reduces the indoor temperature, lowers the air conditioning energy consumption, improves the thermal comfort, it reduces the urban heat island effect, or increase the roof lifespan. Now, there are different types of roof material which are used in the buildings. You can see in these photographs. This is an RCC roof without any coating. Your temperature goes roughly 52 degrees centigrade. Now, in other side of the roof, you have a white coating, and that's the cool roof. Your temperature on the surface of the roof is only 28.8 degrees centigrade. So you can think what is the drop in the temperature by putting this cool roof paint or coating on the roof. Because when you are looking again what how much heat will enter from the roof to the indoor environment, so this will comes from 28 degrees centigrade, not 52.52 degrees centigrade. So this is basically a special type of painting which actually coated on the roof. Reflective roof coating, these are special paints or coatings applied on the existing roofs to increase the reflectivity. Examples like acrylic reflective coating, silicone coating, white lime wash, easy to apply, low cost, suitable for concrete or metal roofs. Cool roof tiles, it's a special tiles designed to reflect sunlight. Examples say clay cool roof tiles, ceramic coated tiles, reflective concrete tiles. It's a high durability, good reflectance, and these are only used in residential buildings. Single ply reflective membranes, thin reflective sheets installed on the roofs like PVC membrane, thermoplastic polyfin membranes. These are lightweight, waterproof, used in commercial and industrial buildings. Metal roof with reflective coating, like this picture you can see, it's a metal roof, but there is a reflective coating on the roof. Like galvanized steel sheet with reflective coating, aluminum sheet with reflective finish. These are high reflectivity, long life, suitable for warehouse and factories. Green roof, vegetated roof, a roof covered with soil and vegetation, like in this building. On the roof, there are lots of plants, grass, and that also reduce the heat enters inside the building. Insulated roof panels, these are now widely used, the galvanized steel sheet, and there is an insulation like polyethylene foam or expanded polystyrene or mineral wools. So this insulation actually reduce the heat gain inside the buildings. Like in our Assam type building, we have a galvanized steel sheet. Now, if we put this kind of roof panels where the insulation is there inside the steel sheet, so obviously the heat gain through the roof will substantially reduce. This is a cool roof tiles, where tiles are placed on the roof. This is the reflective roof coating which are painted or coated on the roof. And these all basically try to reduce the heat gain inside the roof. Let's look some examples. Say building roof receives solar radiation of 900 watt per meter square. Two roof finishes are used. One is dark roof absorbability 0.85. Another is a cool roof absorbability 0.35. Now let's calculate the heat absorbed by the dark roof and the cool roof and what is the reduction in heat gain due to the cool roof. The formula, the amount of the heat absorbed by the surface Q is what is the absorbability and what is the radiation. So here Q is the heat absorbed, it's watt per meter square. We are looking at unit area. Alpha is the absorbability of the surface. I is the solar radiation watt per meter square. So in this dark group, it's 0.85, radiation is 900. So 0.85 into 900 is 765 watt per meter square. That is the amount of the heat absorbed by the roof. But in case of the cool roof, where absorbability is lower, is 0.35 only into 900, so 315 watt per meter square. So what is the reduction in the heat gain? 765 minus 315, 450 watt per meter square. It's a huge reduction of the heat gain through the roof. And this shows that a cool roof reduces the solar heat gain by about 450 watt per meter square, and that helps to make the building cooler and it also helps to reduce the air conditioning energy use. Let's look another example. A building roof has an area of 150 meters square and is exposed to the solar radiation of 900 watt per meter square. The roof is coated with a reflective material having a reflectivity of 0.7. The roof also has an insulation with a thickness of 40 mm. Thermal conductivity of the insulation material is only 0.03 watt per meter Kelvin. The indoor temperature is kept at 25 degrees centigrade and outdoor surface temperature is 45 degrees centigrade. Now calculate the solar heat absorbed by the roof, determine the heat transfer through the insulation, and estimate the effective heat enters the building. Now solar heat absorbed, we know here area is given, so that's why alpha into I into A. 0.3 is the thermal conductivity, 900 into 150, that's the area, is 40,500 watt. Now total incoming solar is a 900 into 150, 135,000 watt. Now only 30% absorbed, rest is reflected, and reflective coating rejects 135 minus 40.5, 94.5 kilowatt amount of the heat. And this is a huge number. Now when we are looking the insulation, how much heat will transfer through the insulation? So in that case, equation Q is K into A into delta T divided by the L. K is the thermal conductivity into 150 area. Delta T is 45 minus 25 and L is the thickness of the insulation material, that is 40 mm. So through the insulation, heat transfer is only 2250 watt. So insulation restricts the heat flow drastically. Even though 40.5 kilowatt is absorbed, only 2.25 kilowatt is passes through, and that goes inside the building. So the effective heat enters the building in a steady state. Actual heat enters the indoors due to the conductive heat transfer, and that is only 2250 watt. So now you can think this is the amount of the radiation falls on the roof, 135,000 watt. Due to the cool roof, this that has reduced to 40,500 watt. Then we have put an insulation that again reduce the heat enters to the room, inside the room is only 2250 watt. So if there is no cool roof, so this amount would have been comes inside the room, 135,000. Now due to the cool roof and the insulation, your heat enters inside the room has come down only to 2250 watt. A building has a flat roof of area 100 meters square exposed to the solar radiation of 900 watt per meter square. Now there is a conventional roof where absorbability is 0.85 and overall heat transfer coefficient, that's the U value, 3.5 watt per meter square Kelvin. Another case 2, which is a hybrid cool roof where reflectivity is 0.7, there is an insulation thickness 40 mm, thermal conductivity 0.03 watt per meter Kelvin, and same indoor temperature is 25 and outdoor surface temperature is 45. For the what we want to do, task, calculate the solar heat absorbed, determine the heat transfer into the building using the U value. This is for the conventional roof. Similar for the hybrid cool roof, and later on we need to compare these two results. So the conventional roof, the solar heat absorbed is alpha I into A. Absorbability is 0.85, 900 into 150, so 114750 watt. Now that overall heat transfer coefficient is 3.5. So how much heat transfer into the building? Q conduction or Q conventional, this is conventional, UA into delta T. So 3.5 into 150 into 20. So this will come roughly 10,500. Delta T is 45 minus 25, that's why 20. So the large solar heat is absorbed. Due to the poor insulation, 10.5 kilowatt enters inside the building. Now let's look the hybrid cool roof. Where reflectivity is given zero point 0.7, so absorbability is zero point 0.3. So in case of the hybrid, it's a zero point 0.3 into 900 into 150 is only 40,500. Now there is an insulation 40 mm, thermal conductivity 0.3, and then Q is 2250 watt. So solar absorption reduced significantly to 40.5 kilowatt. Insulation again restricts the heat and only 2.25 kilowatt enters. Now if you compare these two data, so reduction in heat gain, conventional and hybrid, is 8.25 kilowatt. Percentage of reduction is, you see, 78.57%. So the conventional roof, high absorption, high transmissions, it's inefficient process. Whereas hybrid roof, due to the reflection, solar gain reduction, due to the insulation, conduction reduces, and this dual mechanism actually translate large amount of energy savings. This is another building replace a conventional roof with a hybrid cool roof, reflective coating plus insulation. And the modification results in reduction of the heat load of 8.25 kilowatt entering the building. Now the building is air conditioned with the following parameter. The air conditioner system, the coefficient of performance COP 3.5, daily operation 8 hours per day, number of cooling days per year 300 days, that means your operation days is 300. Electricity cost is rupees 8 per kilowatt hour. Calculate the electrical power saved due to the reduction in cooling load, daily energy saving, annual energy saving, and annual cost saving. Now, what is the electrical power saved for an air conditioner? COP means cooling load divided by the electrical power. So, the electrical power is the cooling load divided by the COP. The cooling load is 8.25 kilowatt divided by the COP. So, it is actually the electrical power 2.36 kilowatt. So the AC now consumes 2.36 kilowatt less power due to the reduced cooling demand. So what will be the energy savings? You know the number of hours per day, number of days per year. So multiply, it gives 5,664 kilowatt hour. Cost saving, electricity cost is 8 rupees. Multiply with the energy saving into cost, it gives you 45,000 approximately per year. So the cooling load reduction directly translates to electricity savings. Higher COP means lower electricity consumption, and hybrid cool roofs significantly reduce the peak load demand. Now, if I look on the payback period in this case, the cost of reflective coating is 120 per meter square. Cost of the insulation rupees 380 per meter square. The roof area is 150 meters square. What will be the payback period? So the initial investment 120 plus 380 into 150 meters square area. So it is 500 into 150, 75,000. What was the annual saving? 45,000. So your payback period is only 1.66 years. It's a very low payback period, highly economically viable. Now let's look the conduction process. The heat flow rate through the building enveloped by conduction is the sum of the area and the U value products of all the elements of the building multiplied by the temperature difference. So generally we write QC is summation I is equal to NC AI UI delta TI. A is the surface area, U is the thermal transmittance or overall heat transfer coefficient. Delta T is the temperature between inside and outside air. I is the building element. NC is the number of components. Now, if the surface is also exposed to the solar radiation, So delta T is actually T saw layer minus T indoor. And already we know what is the T saw layer is T naught plus alpha ST by H naught minus epsilon delta R by H naught. We also need to look ventilation. The heat flow rate due to the ventilation of air between the interior of a building and the outside depends on the rate of air exchange because we are looking at conditioned building. We are going to put an air conditioner in the building. So the QV is rho VAR C into delta T, where rho is the density of air, VAR is the ventilation rate, C is the specific heat of air, and delta T is the temperature difference. If the number of air changes is known, that is the N, number of air changes per hour, and V is the volume of the room or the space, meter cube. So if I replace all these, QV is rho NV by 3630 C into delta T. There are some recommended air changes rates are there. If it is an auditorium, we need to change the air 3 to 6 times per hour. If it is a bedroom, 3 to 6. If it is a restaurant or cafes, 12 to 15 times. So you know the aim if I consider 12. Now let's look the volume of the cafe or the restaurant. Try and get NV. We know the density of the air. C is the specific heat of the air. And what is the delta T you need to maintain. Another important term, what is called solar heat gain. Solar heat gain through transparent element can be written as QS is alpha S, I is equal to 1 to M, AI, SGI, and tau I. Alpha S is the mean absorptivity of the space. You just think of the radiation falls on a glass window. AI is the area of that glass window. I means ith transparent element in meter square. SGI is the radiation falls on the glass surface, and tau I is the transmittivity of the glass surface. M is the number of elements. So if the radiation is more, your QS is more. If the tau is more, QS is more. So if I look at clear glass, but the tau can be 0.8, whereas if I look at some coating on the glass surface, your tau can be comes down to 0.3, and that means your solar heat gain through the glass element will also comes down. Internal heat gain already we have discussed. Here we basically look the number of people into the heat output rate, rated wattage of the lamps, and the appliances load in terms of kilowatt. Here we are not taking too much complicated. We just simply looking the what is the wattage or rating of the lamps or the loads, and we'll just add it. There is another term called evaporation. The rate of cooling by evaporation, say roof pond, fountains, or human precipitation. So QEV is into M into L. M is the rate of evaporation, and L is the latent heat of evaporation. Now let's be this understanding can be clear by having an examples. Say let's look a wall of an area 12 meters square, separates the indoor and outdoor environments. Outdoor air temperature is 34 degrees centigrade. Radiation falls on the wall 750 watt per meter square. Surface absorbability is 0.65. External heat transfer coefficient. So this is because due to the wind speed is 22 watt per meter square Kelvin. Indoor design temperature is 25 degrees centigrade. Overall heat transfer coefficient of the wall is 1.6 watt per meter square Kelvin. Let's estimate what will be the cooling load through the wall. So here we know the outdoor temperature, we know the surface absorbability, we know the radiation, we also know the heat transfer coefficient, external heat transfer coefficient. So T saw layer T naught plus alpha into I into H divided by H naught. I am omitting that minus term because it's a vertical wall. So that term will not be very effective. When you consider the roof, that term will come. So T saw layer is 34 plus 0.65 into 750 by 22. It comes 56.16. So T saw layer is 56.16 degrees centigrade. Physical meaning, the wall surface temperature will be 56 degrees centigrade. So you see here ambient or outdoor air temperature is only 34, but when we are looking the wall, the temperature has increased to 56 degrees centigrade, because that temperature will be important, that how much heat will be comes inside the room. So what will be the heat gain? Now Q is equal to U into A into delta T. Here delta T is T sol layer minus Ti. U is known 1.6 into area 12 meter square, 56.16 minus 25, so 598. So the cooling load through the wall due to the conduction is 598. If we look another example the same way, we can try to find out what is the T shaw layer, and then we are getting what is the temperature or heat gain through the roof. Let's look the U value calculation. This is a brick wall of thickness 19 centimeter. It's plaster on both the sides with 1 centimeter thick cement plaster. The thermal conductivity of plaster and bricks are given. The inside and outside surface heat transfer coefficient are also provided. You see, this is the wall. This is a brick wall. There is a plaster on outside and the inside. The brick wall is 190 mm or 19 centimeter. Plaster is 10 mm or 1 centimeter. The thickness are given. The thermal conductivity, the K1 is in inner plaster, is 0.721 watt per meter Kelvin. K2 is the brick wall thermal conductivity, and K3 again the exterior plaster. Both the plaster are the similar material, so the thermal conductivities are also similar. Now, surface heat transfer coefficient, inside surface coefficient HI is 8.3 watt per meter square Kelvin, whereas the outside surface coefficient H naught is 22.7, because outside there will be more convective heat transfer due to the wind flow, but the inside the air is more or less still, there is not much heat flow takes place. Now what will be the overall heat transfer coefficient of the wall? That means the U value of this one. Now the overall heat transfer coefficient is calculated. U is equal to 1 by R total, where R is 1 by Hi plus L1 by K1, L2 by K2, L3 by K3 plus 1 by H0. So each parameter we are considering. The first, the heat transfer coefficient, then the inner plaster, then the brick wall, then the outside plaster, and then the outside heat transfer coefficient. Now, individual resistance you can calculate, and then what is the R naught? That's the outside. Now, what will be the total? You basically add all these numbers. So, R total is 0.42657. What is the U? Is a reciprocal of the R total. So, U is 1 by R total, and this is 2.34. So, the U value for this particular brick wall is 2.34 watt per meter square Kelvin. Your job is, can I manipulate this number, or can you reduce this number by putting an insulation, making the wall thickness high, making a different kind of paintings, and that's the engineering uh, interest. You see, let's this case. This is a wall consists of 10 10 centimeter concrete and 5 centimeter insulation. The concrete K1 and insulation thermal conductivities are known. Heat transfer coefficient are also known. The same way we are trying to measure or estimate what is the R total. So here 1 by Hi, that's the indoor. This is L1 by K1, that's the concrete. Then L2 by K2, that's the insulation. And 1 by H naught, that's the outside heat transfer coefficient. So if I look the total resistance, we are getting 1.4738. So reciprocal of this value is a U, and you see your U value has come down 0.68 watt per meter square Kelvin. So in earlier case it was 2 point something, Here we have reduced it 0.68. So your heat gain through the wall will also come down. A building has the following surface exposed to the outdoor environment. Your roof 50 meter square area, U value is 2.8 watt per meter square Kelvin. Wall is 40 meter square. Your U value is 2 watt per meter square Kelvin. Indoor design temperature is 25 degrees centigrade. During a summer afternoon, the soil air temperature, roof 52 degrees centigrade, wall 38 degrees centigrade. You need to measure what is the heat gain through the roof and the wall and compare the heat gains. The same formula, U is equal to U into A into T sol air minus Ti. So heat gain through the roof, here 52 degrees centigrade, indoor temperature is 52 degrees centigrade, that's the roof sol air, indoor is 25, U value is 2.8. So 2.8 into 50 into the temperature difference 27 is 3780 watt. Whereas in case of the wall, your delta T comes down to 13. This is area has come down to 40 and U value is 2. So 1040 watt. So roof heat gain is approximately 3.6 times higher than the wall heat gain. And this is generally most of the RCC building, if the roof is exposed to the solar radiation, so the maximum heat gain takes place through the roof rather than the wall. This is a room and we have given all the details and you please have a look these examples. This will give you more understanding how actually we look the building cooling load estimation. Here we have the radiation data on all the different types of walls, south wall, east wall, north wall, west wall, again on the roof, on the windows. We also have the U value for windows, that's the glazing, wall, roof and door. What is the outside average temperature? This is a steady state method. It's an approximation. Here we are not looking the temperature variation throughout the day or the solar radiation variation throughout the day. So what basically we are looking here, we are taking into consideration the delta R, that's for vertical surface. This is not vertical, this is for horizontal surface, that's wrong. This is delta R0 for vertical surface. We try to understand T sol south, T sol east, T sol north, T sol roof, and then what is the conduction, heat gain through conduction. Then we look what is the internal heat gain, what is the ventilation heat gain, and the total heat gain, say 4.21 kilowatt. What does it mean, 4.2 kilowatt heat gain? Now, if this room is to be cooling load, the required AC capacity would be 4.21 divided by 3.517. 3.517 means 1 ton of refrigeration means 3.517 kilowatt. So that ratio we are looking. So it gives 1.2 ton of refrigeration. So this room we typically requires about 1.5 ton of refrigeration air conditioner. So basically we try to look how to estimate the cooling load and based on the cooling load, how we can translate in terms of ton of refrigeration because that's the number we generally need when we are going to purchase a for a air conditioner. Now
Sir,
let's
from
look.
here only. From here
Yeah,
we can buy, sir. With this calculation, we can buy air conditioner, sir. With this
yeah.
values.
This will gives you the actual. Generally, we go to the market and we tell this is the room size. What will be the air conditioner size?
Yes,
So
sir.
they
Yes,
will
sir.
tell you you take a 1.5 ton or you take a 1 ton. 1 ton means 1 ton of refrigeration.
Yes, sir.
1.5 means 1.5 ton of refrigeration.
Yes, sir.
Now let's look the thermal performance study of natural ventilated building. This all the earlier calculations, those are for the condition building, where we try to understand how we can reduce the cooling load or what will be the actual cooling load, or how you can make an optimization based on the U value of the wall, whether you are looking a roof or a cool roof. Your whole objective was how to reduce the cooling load. And if the cooling load reduced, then that will help you to reduce your electricity consumption. Here, these are natural ventilated building where there is no artificial cooling systems such as air conditioner. And these buildings rely on natural ventilation, passive cooling, and climate responsive design. So here the objective of the thermal performance study, we try to understand what is the indoor thermal comfort, analyze the heat gain and heat loss, assess the ventilation effectiveness, can you improve the passive cooling design or the reduce the energy consumption in building. So the benefits of natural ventilated building is lower energy consumption. There is no, as such, there is no cooling load. But when we look a mixed mode building, or we can have fan, improve the indoor air quality and sustainable building design. And these buildings are very common in our country. Now, steps in the thermal performance study, you need to select a building and the climatic condition. You install the measurement instruments like data logger, which measures the temperature, humidity, wind speed. Record the indoor and outdoor parameters, analyze the temperature and airflow patterns, compare the results with comfort standards, and you recommend what kind of design improvements are required. So this is a study of what we have done in the natural ventilated building in Tejpur, Imphal, and Cherrapunji. And this study also includes the objective measurement like temperature, relative humidity, and illumination, and subjective measurement, what is the occupant thermal sensation. In the last day class, we are talking about the ASRE thermal sensation scale. So we conducted 25 days in each season for four different seasons like January, April, July, and October. The measurements takes between the 6 o'clock to 19 o'clock. Parameters recorded air temperature, relative humidity, and illumination level. And the occupant survey, which was the subjective measurement, 150 houses surveyed, 50 houses in each location. Occupants are rated through thermal sensation using the ASRE 7-point scale, and extensive interviews conducted to understand the adoption strategy and the perception. And whole objective of the study was determine the range of comfort temperature in natural ventilated building. This is a typical data for January month in Tejpur. You can see the outdoor temperature and the indoor temperature variation. The pink color is the outdoor temperature and the blue color is the indoor temperature. You can see the drop. The This is the maximum for a particular day. This is the maximum temperature, outdoor temperature. Whereas the indoor temperature maximum is this. So there is a drop, and this is the your time lag or the decrement factor. We can calculate the decrement factor. Based on this understanding, what we trying to understand what is the time lag, and based on the thermal sensational scale, we try to find out what is the comfort temperature. We plot all this, and at the end, if I need a single number, so for warm and humid climate like Tejpur, people feels comfortable or temperature is neutral means the people doesn't feel cold or doesn't feel hot at 26 degree. Cool and humid is 24 degree and cold and cloudy is 22 degree. Now you can see that these numbers are different. That means in Shillong, the people will feel comfortable at 22 degrees centigrade. But whereas in Tejpur, people will feel comfortable at 26 degrees centigrade. So your comfort temperature are not constant or not same in all the climatic zone. The comfort temperature will also depends at which climatic zone you are discussing. The next part is the building performance analysis. In this earlier case, we did on steady state basis model. Now, if we look at dynamic model or your solar radiation data, you are looking from morning to evening, the ambient temperature data you are looking the morning to evening, that variation of the data, if you want to use, then you need to look some computer simulation data. So this building performance analysis, basically we try to answer how much energy does the building consumes? Is the indoor temperature comfortable for occupants? How effective is the HVAC systems? How walls, roofs, and windows are providing proper insulation? So the major objectives: the energy efficiency, thermal comfort, indoor air quality, and the environmental sustainability. So there are different type of analysis: thermal performance, like what we talked about there; energy performance, evaluate the total energy consumption of the building, which includes the HVAC load, lighting load, equipment load, and generally simulation tools are used. You can also have daylighting performance, analyze the natural lighting availability inside the building, which will also helps us to reduce the electricity consumption, improves occupant productivity. We can also look indoor environment quality or HVAC system performance. There are methods: analytic calculation, computer simulation, or field monitoring. So the energy saving can reduce the building energy consumption by 20 to 30% by having the building performance analysis. It helps to improve the comfort level. It also helps to HVAC system design or makes us to choose what is the correct air conditioner system capacity in terms of ton of refrigeration. It helps in sustainable design, supports green building certification. So there are different tools out there like Energy Plus, EcoWaste, Design Builder, EcoTech, Open Studio, and Transys. These are the different tools. There are different advantage, disadvantage of the tools, obviously. What are the steps involved in the building performance simulation? First is the objective. What we are going to do. Identify the purpose of the simulation. Estimate the heating and cooling load. Evaluate the energy consumption. Assess the thermal comfort. Optimizing building design. Study the daylighting and ventilation. You need to collect input data like building geometry, building materials, weather data, and the internal loads. Then we need to develop the building model. Virtual model for the buildings is created using the simulation tool. This model includes the building envelope, thermal zoning, HVAC systems, lighting systems. You run the simulation, and the simulation will calculate the heat transfer through the walls, solar heat gain, indoor temperature variation, energy consumption, HVAC performance. This can be hourly analysis, it can be daily analysis, or annual energy performance. Analyze the simulation results. Typical output would be heating or the cooling load demand, energy consumption, indoor temperature profile, or thermal comfort indices. You need to design optimization where we try to look, can we increase the insulation thickness of the building, of the wall? Can we change the glazing? Can you have another shading device? Or ventilation can be improved? And after that, you will basically optimize the HVAC systems. And then the final decision in the implementation in terms of energy efficiency, thermal comfort, cost effectiveness, and environmental performance. And this optimized design is then used for actual building construction or retrofitting. If we look at typical simulation tool like Transys, which is basically transient system simulation, it is a dynamic simulation software used to model and analyze the thermal and energy performance of building. It is a modular simulation tool that performs transient, means time-dependent analysis of thermal systems, such as buildings, solar energy system, HVAC systems. Unlike steady-state model, transits can simulate hourly or sub-hourly variation in system performance. The component of the Transys Simulation Studio, that's the graphical interface used to connect the system components. Build, create the building models, defining the wall, roof, and windows. Type library. There are predefined system components are there like type 56 building model, type 1 solar collector, type 4 storage tank. Weather data processor use the input climatic data such as solar radiation, temperature, humidity, and wind speed. This is basically used for building performance analysis, solar energy systems design, HVAC systems optimization, and at the end, net zero energy building design. Here, step by step process for the building simulation using the tranches. Simulate a single zone residential building and evaluate hourly cooling load, indoor temperature variation, effect of solar radiation. Say location is Guwahati, simulation is 24 hours. Step 1, define the system architecture. Step 2, weather data point. Step 3 is the building modeling. Step 4, the heat balance equation. Step 5, the transist connection, that's the simulation studio. Solar radiation is connected with the building surface. Ambient temperature is connected as an external node. Then the simulation settings, run the simulation and the results. So indoor temperature profile, like at 6 a.m., it tells indoor temperature will be 27 degree, 12 p.m. 32 degree, 3 p.m. 34 degree. And based on that, you can have a cooling load estimation, and that gives you 4.9 kilowatt. That's the load. So we can convert in terms of ton of refrigeration. We can have a profile data, indoor temperature profile data, cooling load profile data. So this is the scale in terms of time in hours. So you need maximum cooling at say 2 o'clock or 3 o'clock, and then it comes down. This is the indoor temperature profile because you have a very high temperature during that 2 o'clock or 3 o'clock. Now you can have the optimization strategy. You try to reduce the window U value. So that will reduce the lower heat gain. You try to add a shading device. Solar gain reduced by 30 to 50%. You increase the thermal mass, so that delay the peak load. So that optimization you can do if you have some baseline data and then try to optimize how your building can be more energy efficient. We have come to the end of this class. Basically, we try to understand the heat gain and the heat loss of a building. There are basically four parts of the heat exchange: conduction, convection, radiation, and evaporation. We try to understand the building wall geometry and how we can estimate the U value, how we can reduce the U value by manipulating the thickness, putting up the insulation. And that will basically reduce the cooling load demand of the building. The learning outcomes: how do buildings maintain a stable indoor temperature? How do design and material choices impact the energy efficiency? And what design factors improves a building's thermal performance? In next class, we'll discuss on energy conservation building codes and building rating tools. Thank you.